on homework 4, where you're setting up an x and y direction, that the normal force is often shared, okay? Because the force of friction couples the force perpendicular to the surface to the force parallel to the surface. The harder you push two things into contact perpendicular to the surface, the more force you will have parallel to the surface, okay? Okay, so with that in mind, that's the easier force. Notice here that it's not at all velocity dependent or anything, so as long as you're in motion, you can use this, which means that it's a constant force. So that slips in very easily with all your other forces. Let's go ahead and just do another force problem and see how that might go. Let me go ahead and clear this off. I think you have something like this on your homework, so I don't want to give away too much. But let me kind of sketch out something here. I'm going to have a frictionless surface along which I have an object sliding at speed v, and then it hits a friction patch. And that friction patch, I'm going to say the roughness of it is characterized by mu k. Of course, it's really a roughness interaction between the surface and the bottom of the object, but for the purposes of laziness, it's the roughness of the friction patch. These are my givens, v and uk. Now my question is going to be, find an expression for the stopping time of the object once it arrives at the friction patch. So once it arrives at the patch. Okay? So, any questions on the setup before I start knocking it out?
What about the mass?
Don't need the mass. Can't get too hung up on things that aren't given. Just put them in, and they'll drop out later. Okay? Any other questions? Okay, so let's follow the recipe. Step 1, object of interest. Pretty obvious. It's a sliding block. Okay? Step 2, figure out the forces. All right? Well, when it's over here on the frictionless part, of course, it just has these two. Those two are going to cancel. So what's the net force? 0. So what's the acceleration? 0. So whatever velocity that thing has, it'll maintain it until, of course, it gets to the friction patch. So when it hits the friction patch, it's still going at a speed v. It maintains that speed until it hits the friction patch, and then, in addition to the two forces we already have, we now, of course, start to pick up a force of friction, of kinetic friction, against the motion. So now we have 3 forces. All right, I think that's step 2. Step 3, let's decide some axes. We should pick the axes based on the acceleration. So which way is this thing going to accelerate? There's going to be a net force and acceleration against the motion. So let's pick one of our axes to be horizontal. And so we'll pick them like that. Not because we always pick them like that, but because we want one of our axes to be along the direction of the acceleration. In this case, I picked the axis to be against the acceleration, but that's okay. The point is that our acceleration will be all x, but there will be no y acceleration, right? So we purposely want all of our acceleration to be along a single axis. Okay, what's next? Step 4, we'll break the forces into components along those axes. Okay, don't have to do that because they already are. There's no SOHCAHTOA needed. And then we go ahead and move on to step 5. F net x equals max. F net y equals may. We'll plug in those components. Along the x direction, I guess let's do the y direction first. Dot, 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 n equals mg. Okay? Hopefully you know that. That's old news. And then the x direction, we have a single uncontested force. It's in the minus direction. And its magnitude will fill in with that new law that we just found out. The force of friction will be dependent on mu k and the normal force. Now, this is an opportunity for you to see how there's that coupling, right? Because what we can do is recognize that the normal force is mg. So we get minus mu k mg equals max. And we get the x acceleration, looks like that. It's minus simply, of course, indicating that it is to the left against the motion. That's why it's going to slow down. The net force and acceleration are against the motion. So now we go ahead and solve for what we want. Well, we were asked for the stopping time. Well, of course, this is adding an extra little bit at the end, which is just some good old kinematics, right? So now we can tie this into our kinematics equations. Go ahead and put down our 5 variables in no particular order. We have the acceleration. That's in the negative direction. We have our initial velocity. That's in the positive direction. So notice I'm setting signs here. You got to set your signs here. What's my final velocity? 0. I'm trying to find the time to stop, right? Don't know, don't care about the displacement, although it would be an excellent question on its own. How far does it slide before it stops? Notice, by the way, my positive velocity better have a negative acceleration, otherwise I would never be able to come to a stop, right? So a common mistake here is you forget all about signs. You accidentally have an acceleration that's going with the velocity, and you're going to speed up indefinitely. That's not what happens here. Okay, so we picked the equation, equation number 1. Go ahead and plug in everything, and just to spare you the suspense, you get this, which again is not intended to be a derivation. It's a symbolic solution to this problem. Not a whole lot of limits we can check with this, because there's no addition or subtraction there, but we can at least check the proportionalities. According to this, t is directly proportional to v initial. So this is t stop. So according to this, if you hit the friction patch going faster, sorry, I called it v, just v here, so that's what it is. So according to this equation, if you hit the friction patch going faster, should it take more time or less time to stop? More time. Is that what that proportionality says? It does, right? In fact, it tells us that they're directly proportional, which means if you hit it going twice as fast, it'll take you twice as long to stop. Hopefully not surprising, and we can even get the exact relationship. So that would be an example. This also tells us t is inversely proportional to mu k. So it tells us that if the surface gets rougher, what happens to the time to stop? Get bigger or smaller? Smaller. Does that intuitively make sense, right? If it gets rougher, it takes a shorter time to stop? Yeah, and in fact, we know the exact relationship. If we double the roughness, what will happen to the time? It's half. It'll take half as long to slide this stop. Okay, this is the beauty of proportionalities, is that it not only tells you what are the relationships, but exact in general terms, but in exact terms. We can even go one further. We can say t is proportional to 1 over g. Now, G is of course not normally up for debate, but let's say we went to a planet where the pull of gravity was stronger, okay? According to that, if we went to some planet where the gravity pull was stronger, the time to stop would be less. Makes sense, right? Because gravity is pulling that object harder into the surface, and it's going to increase the friction. Okay? So there's an example of another application of these laws, not just force of friction, but all these other laws, all these other older forces as well. Another example of symbolic solutions, and a way to check your symbolic solutions make sense with proportionalities and also get an idea of the exact relationships. Okay, are there any questions on this example? Okay, so that pretty well covers kinetic friction. It's nice enough, of course, to be constant or approximately constant, so that throughout the slide, we can count on it being a constant force. Because we'd have an issue if that force was changing, then the force was changing, the acceleration is changing, and we can't do that, right? Not in this class. We want to do constant acceleration. So now we go over here to the force of static friction. And this has a variable amount of size depending on the circumstance. So let's see if we can, in the next 10 minutes or so, try to gain some understanding of what that's all about. So let's suppose, for instance, that whatever this quantity is, okay, let's say this comes out to be 5 newtons, okay, which means our static frictional force can be anywhere from 0 up to 5 newtons, okay. That is just a range. It doesn't mean that it's always 5 newtons. It means it's somewhere between 0 and 5 at most. So let me give you an example. I'll have an object on a surface. This is static friction, so it isn't moving. But we're going to have some attempts to move it. I'm going to put various pushing forces over on the right, and various frictional forces. I will identify what is the corresponding frictional force on the left. Okay, so let's start with this table. That'll be my object. I'm not going to push on it at all. So how much static friction force is needed to keep it from moving? None. Okay. So if I push 0, static friction doesn't push back with 5. There's nothing to push against. Okay. Now, let's say I push instead. I push horizontally with 1 newton. Okay. Does it move? No, it won't move. How much does static friction force need to exert to keep me from moving it? Is it 5? No, it says 1. So if I push on it with 1 newton, it reacts with only 1, not 5. What happens if I push something with 1 newton and friction came back at me with 5? What would it do? It would come toward me. There's very few things that you push and they come toward you, okay? So I know that this is a formula that you can cling to, like a life raft, without having to, have to think about the situation. But it doesn't mean that it always gives you the frictional force. It tells you what's the most the frictional force can be. Okay? If I pushed with 4 newtons, is it going to move? No. How much friction is needed to keep it from moving? 4, not 5, 4. Okay? If I push with 5 newtons, is it going to move? Well, can static friction push back 5 newtons? Yeah, it can, but now it's maxed out, right? This is maxed out. It can't be any more. So I've run the full gamut here. But in all these situations, the net force is 0, and therefore, the object stays at rest. in all of these scenarios, static friction is able to successfully match what I throw at it. But notice that it does not always flex the maximum muscle, it only does what's necessary, okay? So the common thread here is this. I have that the pushing force is acting, let's call this plus. The pushing force is acting to the right. The frictional force is able to cancel it. The net force and acceleration is 0, okay? We can throw it over here like this. And we could even get a little bit more generic. Instead of saying F push, okay, that implies that there's a human being behind it. But really, there's forces parallel to the surface trying to move the object. And if they fail, it's because the static friction killed them all, okay? This right here is often the best way to figure out what is the force of friction. You know you have 17 different forces acting to try to move it along a surface. It doesn't do a thing. Therefore, friction must have successfully killed them all, okay? So there's not a whole lot of difference. For instance, if we had a surface like this, we had an object. Let's say we had a force of gravity that's, I don't know, 10 newtons. Let's say we had a pushing force. Let's say that was 2 newtons. How much is the normal force here? It's 12, right? It needs to kill those guys. To prevent motion in the surface, right? To prevent the surface from getting crushed. This is really no different. So over here, let's say I have a force of 10 newtons trying to push it, and a force of 2 newtons trying to push it. If it doesn't move, how much does static friction cancel? Cancel 12. Maybe that's the maximum it can do. Maybe it's not. But if it doesn't move, that's how much it canceled. That's obviously over the cap of what I was just talking about. Okay? The only difference between these two situations is that we assume that the normal force can grow without any limit. It can always cancel off what's necessary. Our surfaces never crush, they never break. This obviously is going to have some kind of limit, right? Because at some point you push something hard enough, you can move it, right? So if you pull hard enough, it will move. So it's kind of similar to normal force in that it's variable in doing its job, but it has a limit. And if you exceed that limit, it will slide. So if all of these are the cases where it's able to cancel off, we could imagine pushing a little more, 5.00000 whatever, 1 newtons, okay? And static friction can't keep up with that anymore. And so what's going to happen? It's going to move, right? So in this case, the net force is not 0, and you will have acceleration from rest. So it's a variable force. Static friction is a variable force. Most of the time, the best way to figure it out is by context of looking what is trying to move it, and if those things are failing, it's because static friction killed them all. Whether it does it with very little of the amount in store, like this, so here we only needed 0 or 1 newton, or if it uses every last drop, is contextual, okay? So I'm going to put a little arrow here. Where is it in this range? As needed. The force of static friction will cancel off the forces trying to move it. The only difference is here is that it has a point at which it gives out, okay? You can calculate the maximum force it's capable of canceling, and if you go above that, then you will move it. And as to what these ingredients are, it's very similar. The amount of maximum force you can get out of static friction depends on the contact force, again, N, just like it used to be, and it depends on the roughness. So there is a coefficient of static friction. You may wonder why it's not the same coefficient, why there has to be two different ratings for the roughness, which seems silly. It's like you're rating the roughness twice. Roughness once when you're not moving, and roughness once when you are moving. So we'll talk about why that is next time. But for right now, I think that's good for today. So we'll pick up some more stuff next time.